Shall I move on to the next verse?
Yes, Doctor.
Okay. What are these? Next, you are going for three different derivations. That is relation between moment of inertia, how moment of inertia is related to kinetic energy of a rigid body, rotational kinetic energy, right? Moment of inertia is related to the kinetic energy of the rigid body, how it is related to the torque acting on a body, how it is related to angular momentum. The first one is, now the initialization is the same. What do you mean by initialization? For all the relation, now you're going for the relation between the rotational kinetic energy and moment of inertia of a body, right? Now how they are going to be related, that's what you are going to derive. For all other derivations, it's the same. Now you are considering, can you see the diagram? You're considering a body of irregular shape, right? Now this body consists of masses m1, m2, m3, etc. up till mn. Now all these particles m1, m2, m3, etc. are lying at a distance of r1, r2, r3, rn, somewhere from the axis of rotation. Are you clear, boys? You are considering a rigid body. Now the initial statement should be by you. You are considering a rigid body consisting of masses m1, m2, m3, etc. up till mn, right? Situated at distances r1, r2, etc. up till rn. From where? From the axis of rotation. Now that will be your first point. So you're describing what is m1, what are the mass and r, the distance. Now, second point, what you need to state is that the entire body is rotating with an angular speed omega. The entire body is rotating with an angular speed omega. Now, what happens is that each and every particle the same angular speed. Suppose if I consider a particle m1, once I'm considering the body is rotating, which means each and every particle of the body is also rotating about the axis. The entire body is rotating about an axis, which means each and every particle is also rotating about an axis. Now let me consider a particle m1. So now this m1 is moving in a circular path about the axis of rotation. Is that clear, boys? So this particle m1 is having a linear velocity v1. Particle m1 is moving with a linear velocity because at every point the velocity keeps on, the direction of velocity keeps on changing. So it's not the magnitude, the direction keeps on changing. So m1 is moving with a linear velocity v1 about the axis of rotation. Suppose if I take m2, m2 is still farther away, m2 is going to move with a velocity v2, with a linear velocity v2 about the axis of rotation. Same way mn will rotate with a velocity v1, vn about the axis of rotation, but all particles will rotate with the same angular speed omega. All particles will rotate with the same angular speed omega, but different particles will rotate with different linear velocity v1, v2, vn, etc. Is that clear for all of you? Is that clear?
Yes, ma'am.
Okay. So now, can someone, Steve, can you start with the statement, or will you start? Consider a rigid body. Just give me the statement. Let others write. Steve. Steve has gone for any meeting.
Okay.
Yeah.
Just 1 second, ma'am.
Okay. You just
Consider. Can I?
Okay, you can state.
Consider a rigid body moving about a vertical axis. M1, M2, and
Okay. Fine. I'll put because I think first part will be tough for you all. So I'll read it out. Or just start with this. Okay. Start with this. Draw a diagram and start with this statement. Thank you. Consider a rigid body consisting of particles of masses m1, m2, mn situated at distance r1, r2, rn from the axis of rotation. Okay. Steve, what will be the second point? The entire body is rotating with an angular speed. The entire body, the body is rotating with an angular speed. Okay. With an angular speed, the body rotates about an axis with angular speed or with angular velocity omega. Okay. With angular velocity Ayush?
Ma'am,
Ma'am,
he's in
there's
the
no Ayush in this class.
Ma'am, he's
Oh,
in
sorry,
11th,
sorry.
he's not here.
Ma'am, 11 Ayush.
Okay, fine. Let V1, V2, etc. up till Vn. Sorry, boys, I'm getting confused with V and C. Let V1, V2, etc. up till Vn. Now, what are these? Can someone tell me what are these V1, V2, etc. up till Vn? What are these, boys? V1, V2?
Ma'am, linear velocities of
Of
each other.
M1, M2, M3, etc. This is how you have to initialize whenever you go for the derivation. This is your initialization. Is that clear, boys? Is that clear?
Yes, ma'am.
Okay. Now, stepwise, we'll derive. We'll go for the derivation. What is the linear velocity of the particle? See, you know, whenever particle moves in a circular path, there is a relation between linear velocity and angular velocity. Because whenever a body moves in a circular path, v is the linear velocity, r is the radius of the circular path, omega is the angular velocity. So the linear velocity of particle of mass m1, what is that? v1 is equal to r1 omega, because all the particles move with the same angular speed. Are you clear with this, boys? Are you clear? Particle m1 is moving with a velocity v1, but angular velocity is omega. m2 will move with a velocity, linear velocity v2, but angular speed will be omega. Correct? Am I correct?
Yes, ma'am. Yes, ma'am. Yeah.
Okay. Harish, Harish, what will be v2?
R2 omega. R2 omega.
Okay, R2 omega. Okay, fine. So what will be Vn?
Rn
What will
omega.
be? Okay, Rn omega. So for all other particles, your linear velocities are V2 is equal to R2 omega, Vn is equal to Rn omega.
Ma'am, rotational kinetic energy, is that the same as normal kinetic energy?
No. We will see. Let us see what it is. Okay. So now first step, you have got an expression for your velocities of each masses. Okay. Can you find the kinetic energy of the first particle? What is the kinetic energy of mass m1? What is the kinetic energy of mass m1? What is the formula for kinetic energy? I'm not talking about rotational kinetic energy. What is the formula for kinetic energy?
half mv square.
Half m1? Half m1?
v1 square.
Okay, v1 squared, fine. Now, what is v1? What is the value of v1 here?
r1 omega.
V1 squared. Okay, v1 is
Yes,
r1
so,
omega. So what is v1 squared?
r1 square omega square.
Correct. Boys, are you all getting this? The next statement should be kinetic energy. Kinetic energy. Kinetic energy of rotations of the body half m1 v1 squared plus this is the total kinetic energy. Okay, fine. Whom should I call? Kritya, what is V1 here? Kritya? Kritya, what is V1 here? What should I substitute for V1? What should I substitute? What is V1? What is V1? The previous one. No? Jopal, what is the value of V1? Jopal, what is V1, boys?
Ma'am, it's R1 omega, right?
Yes,
Okay,
ma'am.
R1, okay, R1 omega, the whole square, half. Shriram, what is V2?
Ma'am,
Sriram also other class.
yeah.
Sorry.
Ma'am, no problem, ma'am. It happens.
One second, I'll. What is V2?
R2 omega.
R2 omega.
R2 omega, the whole square, plus half. Ayan, what is Mn? Sorry, this will be Mn into, what is Vn? What is Vn?
Vn is Rn omega
The whole
whole
square.
square. Yes.
Okay. Now what is that? You solve this, boys. Are you getting this? M1 R1 squared omega squared plus half M2 R2 squared omega squared plus half Mn. It goes on, boys. I have to put that. Rn squared omega squared. Are you all getting this?
Yes, ma'am.
Ma'am, then we have to take half common.
Yeah, we'll I'll ask Derek. Sorry, Dheeraj. Dheeraj.
Yes, ma'am.
Dheeraj, in this expression, can you check the common factor? What will be the common factor here?
Half
Half? Only half? Just see.
and omega.
What is it? Oh, and omega? Omega squared or omega? Dheeraj, is it omega squared or omega?
Ma'am, squared.
Oh, omega squared. So I'll take half omega squared outside. Dheeraj? Dheeraj?
Yes, ma'am. Yes, ma'am.
Okay, now what is left? Because you carry on. I will write what you are going to state now. What is left? This is what is left. First term. Half omega squared I have taken. M1.
M1 R1 R1 square.
Okay, fine. Plus.
M2 R2 square plus
Okay.
Mn
M2.
Rn square.
Okay. Plus it goes on till Mn Rn squared. Fine. Okay. Now, Dheeraj, tell me what is this term, this entire term? M1 Rn squared plus M2 R2 squared plus Mn Rn squared. What is that term? Just see what is moment of inertia.
Can I tell?
It's not a problem, boys. Dheeraj, just check. I is this is that not I is equal to moment of inertia m1 r1 squared plus m2 r2 squared? It goes on up till mn rn squared. Correct? Is that correct, Dheeraj? Fine.
Yes, ma'am.
Dheeraj. Okay, so now what will be? This is my rotational kinetic energy, right? It's not the normal one. It's my rotation because here it was your linear kinetic energy. Now you have introduced omega, so it becomes rotational kinetic energy. So how should I write Dheeraj rotational kinetic energy? Half
Omega square I.
okay, half omega squared I, or I can write half I omega squared. Are you clear? Are you clear with this?
Yes, ma'am.
So this is the relation. Look at this. This is rotational kinetic energy. Rotational kinetic energy is related to moment of inertia. So that is what you wanted. You wanted a relation between the moment of inertia and the rotational kinetic energy. What is moment of inertia? Moment of inertia tells you how difficult it gives a measure the difficulty of rotating a body. How difficult it is for you to rotate a body. That's what is your moment of inertia. So your moment of inertia and the relation between rotational kinetic energy you have derived at. Fine. Anyone who has still a doubt? Boys, anyone who is having a doubt?
Ma'am.
Yes.
Ma'am, before you had drawn two diagrams and put the center of mass passing through the axis of rotation and one not. So which one will be easier to move, ma'am? Like you asked us.
Will you check by yourself, boys? Just check and come back tomorrow. Let me know. Let me know.
Ma'am,
Just check. Let me know, because it is going to get related to the next coming theorems. There are two theorems. Anyway, you're not going to in depth of the theorem because of your revised syllabus. That theorem tells you. Just check. You just do it as a homework or just go for the checking. Anyway, we'll have to come across that topic. Which one is easier for you to rotate from yours?
Ma'am, how do we show the relation between kinetic energy and moment of inertia?
Yeah, kinetic energy is equal to half I. You want to define? You mean you want to define?
Yes, ma'am.
Okay, okay, fine. Okay, if you want to define, then what we'll do is 1 second. We'll go for the empty slide. I'll just write this as K is equal to half I omega square. Suppose if omega is equal to 1 radians per second, clear? Then what happens to your kinetic energy? Kinetic energy will be equal to I by 2. Or I can write this way also. When a body rotates with an angular speed of 1 radians per second, then the moment of inertia is 2 times the rotational kinetic energy of the body. This is also a way, right? The moment of inertia of, whenever you're stating moment of inertia, was the moment of inertia, when the statement comes, it's always about an axis of rotation, because the axis of rotation, the placement of the axis of rotation is very important. So the moment of inertia about an axis of rotation is equal to 2 times the rotational kinetic energy of the body when the body is rotating with an angular speed of 1 radians per second. This is how you define, right? A moment of inertia from your rotational kinetic energy. You want me to make you to write, boys? Boys, do you want me to make you to write the statement? Or
No, ma'am.
okay, you'll understand. So tomorrow's class, what we have to do is same way, we have to relate torque and moment of inertia. How is your torque going to get related? Same way, in a different way you have to move. So how torque becomes equal to I alpha. Right? Next, again you have to go for relation between moment of inertia and angular momentum. So as what you have done, same way we have completed the relation between moment of inertia and rotational kinetic energy. Now we'll have to move on for all these things.
Thank you, ma'am.
This chapter is very, very important from your engineering studies. When you go for your higher, for your professional course, chapters are very important. Thank you, boys.
Thank you, ma'am.
Thank you, boys.
Thank you, ma'am.
Thank you, boys.